Professor Wiles, please accept our warm congratulations for having been selected as the Abel Prize laureate in 2016. To be honest, the two of us, we expected that we would have had this interview already several years ago. You earned fame not only among mathematicians for, and now I cite, your stunning proof of Fermat's last theorem by way of the modularity conjecture for elliptic curves, opening a new era in number theory. This proof goes already back to 1994, which means that we and you had to wait for more than 20 years before it earned you the Abel Prize. Nevertheless, you are the youngest Abel laureate so far. In the time after you finished your proof of Fermat's last theorem, you had to undergo many interviews, I know, which makes our task quite difficult. How on earth are we to find questions that you haven't answered several times before? Well, we should try to do our very best. But nevertheless, in particular in view of our spectators from Norwegian TV, we have to start at the very beginning. And that is in fact in Latin. So now I try to cite in Latin. Nullam in infinitum ultra quadratum potestatem in duos eustem nominis fast est dividere, which means it is impossible to separate any power higher than the second into two like powers. And then he continues, cuius rei demonstrationem mirabilem sane detexi, hanc marginis exiguitas non caperit, which means I've discovered a truly marvelous proof of this, which this margin is too narrow to contain. So this remark was written by the French lawyer and amateur mathematician Pierre de Fermat in his copy of Diophantus Arithmetica somewhere in the 1630s. He certainly didn't expect at the time that he would keep mathematicians, professionals and amateurs alike, busy for centuries in trying to unearth a proof. So could you please give us a short account on some of the serious attempts towards proving Fermat's last theorem until you embarked on your journey, and why was such a simple-minded question so attractive, and why were attempts to answer it so productive in the development of number theory?
So the first serious attempt to solve it was presumably by Fermat himself, but unfortunately we know nothing about it except for what he explained about his proof in the specific cases of n equals 3 and n equals 4, that he showed that you can't have the sum of two cubes being another cube, or the sum of two fourth powers being a fourth power. So he did this by a beautiful method which he called infinite descent, which was a new idea, a new way of presenting mathematics anyway, in arithmetic. And he explained this proof several times to his colleagues in letters, and he wrote it also in the margin was big enough for some of it. But then after this was published by his son after his death, it lay dormant for a while, but was picked up by Euler and others later, who tried to find this truly marvelous proof. And they failed. And it became quite dramatic in the early 19th century. People thought they could solve it. There was some discussion in the French Academy, and Cauchy jumped in and said he thought he could too, and so on. But in fact, it transpired that the German mathematician Kummer had actually written a couple of papers where he explained that the fundamental problem was what's known as the fundamental theorem of arithmetic. That is, in our normal number system, any number can be factorized in essentially one way. So you take the number like 12, it's 2 times 2 times 3. And there's no other way of breaking it up. But in the system of numbers that you want to use to try and solve this Fermat problem, you actually use systems of numbers where this doesn't hold. And every attempt that was made to do it failed because of this failure of unique factorization. Kummer analyzed this in incredible detail. He came out with the most beautiful results. But the end product was that he could solve it for many, many cases. For example, less than n equals 100, he solved it for all numbers except 37, 59, and 67. But it didn't finally solve it. His method actually was the same that Fermat had tried, the method of infinite descent, but in these new number systems. Well, these new number systems he was using spawned number theory, algebraic number theory as we see it today. So it involved developing other number systems where you might try and solve equations instead of just solving it with ordinary integers or rational numbers. And attempts at Fermat carried on but somewhat petered out in the 20th century. No one came up with a fundamentally new idea. Until the second half of the 20th century, number theory moved on, considered other questions, and then in 1985, Gerhard Frey, a German mathematician, came up with a stunning new idea where he took a hypothetical solution to the Fermat problem and rewrote it so that it made what's called an elliptic curve. And he showed, or actually suggested, that this elliptic curve would have very peculiar properties. And he conjectured that you couldn't really have such an elliptic curve. Well, the American mathematician Kenneth Ribbett then actually demonstrated that using this Frey curve, that any solution to Fermat would contradict another well-known conjecture called the Modularity Conjecture. So this conjecture had been proposed in a weak form by Taniyama and refined by Shimura. Was first real evidence for it came from André Weil, who made it possible to check that new conjecture, the Modularity Conjecture, in some detail. And a lot of evidence had been amassed showing that this Modularity Conjecture should certainly be true. So at that point, mathematicians could see, yes, Fermat is going to be true. And moreover, there has to be a proof of it. Because what had happened is that this Modularity Conjecture was not a problem that mathematics could just put to one side and go on for another 500 years. It was there was a roadblock right in the middle of mathematics. It was a very, very central problem. Whereas Fermat, you could just leave it aside and forget it almost forever. This, you could not forget it. So at that point, when I heard Ribbett had done this, that moment I knew, okay, this problem can be solved, and I'm going to try.
Yeah. Could I interject a little about speculation about Fermat's proof, so-called proof? Do you think that he had the same idea as Lamé had the wrong? I mean, assuming that the cyclotomic, integers have a unique factorization.
No, I don't think so. Although the error might be in there somewhere. It's very hard to understand. André Weil wrote about this because all the other problems he considered were to do with curves that were genus 0 or genus 1. And suddenly he's writing down a curve that's higher genus. How is he going to think about it? So I think when I was trying this myself when I was a teenager, I put myself in Fermat's frame of mind, not because there was anything else I could do. I just thought his mathematics from the 17th century I was capable of understanding. Later mathematics probably not at that point. And it seemed to me that everything he did came down to something about quadratic forms. And I thought maybe that would be a way to try and think about it. Of course, I never succeeded, but there's nothing else that suggests he fell into this trap with unique factorization. And in fact, from the point of view of quadratic forms, he understood sometimes there was unique factorization and sometimes there wasn't. So he understood that difference
Okay.
in his own context.
Yeah.
So I think it's very unlikely that was the mistake.
Because, I mean, in the same book by André Weil that you mentioned, Fermat had this a cube minus a square equal to 2 has only essentially one solution, namely x equal to 3 and y equal to plus minus 5.
Yes.
And I think that André Weil speculates that Fermat at that time looked at the ring z plus z square root of 2 and used that unique factorization in that thing. So
z root minus 2, yes.
Yeah,
I think it is, yes.
So, okay.
Yes, he used the unique factorization, but the way he did it was in terms of quadratic forms.
Okay.
And I think he also looked at quadratic forms corresponding to z root minus 6, where there's not unique factorization. So I think he understood. That was my impression at the time, that he understood the difference.
Okay.
So we have already started on your personal mathematical education. I'm curious to know, I mean, you were apparently already interested in mathematical puzzles as a quite young boy. Have you any thoughts about where this interest came from? Is it family or any other influence that you can pinpoint?
Well, I just enjoyed mathematics when I was very young, but I at the age of 10, I was evidently looking through library shelves devoted to mathematics, and I would pull out books, and then at one point I pulled out the book by E.T. Bell, which describes, on the cover, describes this problem and the Volskel Prize and the romantic history of this problem, and I was completely captivated by it.
Was there other things in that book that fascinated you, this book by Eric Temple Bell?
It's entirely about that one equation, really, and it's actually quite wordy, so there is less mathematics in some sense than you might think. Yes. So I think it was more the equation. But then when I found this equation, then I think I must have found other elementary books on number theory and learned about congruences and solving congruences and so on, and other things that Fermat did.
And you did this sort of work besides of your ordinary school career?
Yes, I don't think my schoolwork was too taxing from that point of view.
Okay. So was it already clear for you at that time that you had an extraordinary mathematical talent?
I think I had certainly mathematical aptitude and obviously loved to do it, but I don't think I felt I was unique, and I don't believe I was in that school. I think there were others who had just as strong a claim to be future mathematicians, and some of them have become mathematicians. So. And
it was already clear for you very early on that you would study mathematics and getting into a mathematical career?
No, I don't think I really understood you could spend your life doing mathematics. I think that only came later, but certainly studying it as long as I could. I'm sure as far as my horizon was, it involved mathematics, yes.
You then started to study mathematics as a student in Oxford, and back in 1971, is that right? Yes. Can you tell us a little bit about how that worked out? Were there any particular teachers, any particular areas that were particularly important for you?
So before I went to college, actually in high school, one of my teachers had actually had a PhD in number theory, and he gave me a copy of Hardy and Wright. And I'd also found a copy of Davenport's Higher Arithmetic, and these two books I found very, very inspiring in terms of number theory.
So you were on track before you started to study?
Yeah, I was on track before, and in fact, to some extent I felt college was a distraction because I had to do all these other things, applied maths and logic and all these things, and I just wanted to do number theory, and you weren't allowed to do number theory in your first year, and you didn't really get down to it till your third year. So.
But you were not interested in geometry as much as in algebra or number theory?
No, primarily in algebra and number theory. I mean, I was happy to learn these other things, but I really was most excited about the number theory. And so I think my teachers enabled me to take extra classes in number theory, but there wasn't that much on offer. I think at one point I even decided all the years of Latin I'd had to do at school, I should put it to good use and try to read some of Fermat in the original, but I decided that was actually, that was too hard. Because even if you've translated the Latin, the way they wrote in those days wasn't in algebraic symbols very much, so it was quite difficult.
Yes.
So it must have been a relief when you then went to Cambridge to start studying really number theory with John Coates.
That's right.
As your supervisor.
So I went there. You had a year, preliminary year, in which you just studied a range of subjects, and then I could do a special paper. And John Coates was not yet at Cambridge, but I think he helped me, or maybe over the summer after it, I met him, and then I started working with him right away, and that was just wonderful. The transition from undergraduate work, where you're just reading and studying, and the transition to research was the real break for me.
Yeah.
It was just wonderful.
And it was John Coates, I assume, who initiated you to work really on elliptic curves.
Absolutely.
And
yes.
Iwasawa theory,
Yes.
and so on.
He had some wonderful ideas and was generous to share them with me. And
You told John Coates that you were interested in the Fermat problem, I gather.
I probably did, and he probably warned me. No, it's really true that there hadn't really been any new idea since the 19th century. People were trying to refine the old methods, and yes, there were refinements, but it didn't look like the refinements and the solution were going to converge. It was just too hard that way.
Right. But at that time, when you started working with John Coates, you had no idea that this elliptic curve should turn out to be really the crucial.
No, it's a wonderful coincidence. And the strange thing is that the two things in a way that are most prominent in Fermat that we remember are his work on elliptic curves and this, I mean, for a number theorist. Because this equation you mentioned, y squared plus 2 equals x cubed, an elliptic curve.
Right, right.
It's
Yes.
same thing.
Could you spare a few seconds to explain what an elliptic curve is and how it is the theory is developed by means of Iwasawa theory?
Yeah, so for a number theorist, the life of elliptic curves started with Fermat as equations of the form y squared equals a cubic in x. And the cubic in x would have rational coefficients. And then the problem is to find the rational solutions to such an equation. And what Fermat noticed was, besides the kind of result you get if you look at integer solutions, sometimes you can prove there are very few and sometimes even say exactly what they are. In contrast with rational solutions, you could sometimes start with one or even two and use them to generate infinitely many others. And yet sometimes, as actually, it's not obvious, it is an elliptic curve, but the case n equals 3 of Fermat's last theorem is in fact an elliptic curve in disguise. Sometimes you could show there are no solutions. So you could have infinitely many and you could have none. So this was already apparent to Fermat. And so people studied these equations, and then at the turn of the 20th century, Poincaré actually realized that you could study these. Well, sorry, I'm jumping ahead. We should say in the early 19th century, one studied these equations in complex numbers. And then Abel himself comes in at this point, studying elliptic functions. And they were very well understood in terms of doubly periodic functions in the early 19th century. But that's the complex solutions to the equation in complex numbers. The solutions to the equations in rational numbers were studied actually by Poincaré, and there was what's now known as the Mordell-Weil group, was proved by Mordell and then Weil in the early 20s, that the rational points on an elliptic curve form a finitely generated abelian group. That is, from Fermat's language, you could start with a finite number of solutions and using those generate all the solutions using what he called the chord and tangent process. So that that group, okay, you now know the structure is a very beautiful algebraic structure, but that doesn't actually help you find the solutions. So no one really had any methods for finding the solutions, any good methods, until the conjectures of the late 50s, which emerged from Birch and Swinnerton-Dyer. So there are two ways of formulating it. One is somewhat analytic, and one is in terms of what's called the Tate-Shafarevich group. But basically, the Tate-Shafarevich group gives you the obstruction to finding an algorithm for finding these solutions. And the Birch-Swinnerton-Dyer conjecture tells you there's actually an analytic method for analyzing this so-called Tate-Shafarevich group. And if you combine all this together, ultimately, it should give you an algorithm.
And you worked already on Birch and Swinnerton-Dyer when you were a graduate student together with John Coates.
Yes, that's exactly what he proposed working on, and we got the first results in this analytic link between solutions and what's called the L function of the elliptic curve in certain special families of elliptic curves.
This was complex multiplication.
Exactly. So these were the elliptic curves with complex multiplication.
Was this really the first result concerning this Birch-Swinnerton-Dyer conjecture?
I think it was the first one that treated a family of cases rather than an individual case. There was a lot of numerical data on individual cases, but this was the first infinite family of...
And this was over the rational numbers, right?
Yes.
We should just mention that this conjecture, the Birch and Swinnerton-Dyer conjecture, is one of the Millennium Clay Prize.
Yes.
Which, if somebody could solve it, would earn this somebody $1 million, right?
That's right. I think it's appealing partly because its roots are in Fermat, just like the Fermat problem. So it's another elementary to state problem concerned with equations of, in this case, very low degree, which we can't master and which Fermat initiated. So I think it's a very appealing problem.
And do you think it's in reach somehow, that we have the tools somehow, that if somebody is daring enough, or do we have to wait another 300 years?
I don't suppose it's 300 years, but I'm afraid I don't think it's the easiest of the millennium problems. So I think it's still we're lacking some things, which, whether the tools are all here now, they may be. I mean, that is always the problem with these really difficult problems. It may be that the tools simply aren't there. No, I don't believe anyone in the 19th century could have solved Fermat. Certainly not in the way it was eventually solved. There was just too big a gap in mathematical history. You have to wait another 100 years for the right pieces to be in place. So you can never be quite sure with these problems whether they are accessible to your time. That's in fact what makes it so challenging. If you've got the intuition for what can be done now and what can't be done now.
You mentioned the Tate-Shafarevich group,
yes.
And in that connection, the Selmer group also pops up. And Selmer, of course, was a Norwegian mathematician.
That's right, yes.
And I think it was Cassels that named this group that occurs, the Selmer group. Could you say in a few words what the Selmer group, how it's related to? Is that too technical?
It is technical, but on the other hand, I can probably say. So basically, the Selmer group, what you're trying to do is to find the rational solutions on the elliptic curve. And the method is you take the points on the elliptic curve, suppose you've got some, and you can, if you like, generate extensions from those. So when I say generate extensions, you can take roots of those points on the elliptic curve. Just like taking the nth root of 5 or the cube root of 2, you can do the same thing on an elliptic curve. You can take the nth root of a point, so all points that times n give you the point you started with. They generate certain extensions of the number field you start with, so of the number field Q. So you can put a lot of restrictions on those extensions. And the Selmer group is basically the smallest set of extensions you can get, putting on all the obvious restrictions. And so you've got the group of points. They generate some extensions. That's too big. You don't want all extensions. You cut that down as much as you can using local criteria, so using p-adic numbers. You cut it down as much as you can, and that's called the Selmer group. And the difference, essentially, between the group generated by the points and the Selmer group is the Tate-Shafarevich group. So the Tate-Shafarevich group gives you the error term, if you like, in trying to get the points from the Selmer group.
I see. But Selmer's paper, he of course looked at the equation, the Diophantine equation, 3x cubed plus 4y cubed plus 5z cubed equal to 0.
Mm-hmm.
And he showed that it had no, just a trivial solution in the integers, but
yes.
mod m, it had non-trivial solution for all m.
Yes.
And well, is there? Why did Cassel call it? I mean, in Selmer's paper.
Yes, there's quite a subtle relationship between these. So what happens is you're actually looking at one elliptic curve, which in this case, I've forgotten exactly which curve it comes out to be, but it would be equivalent to x cubed plus y cubed plus 60z cubed equals 0. And that's an elliptic curve. And the Tate-Shafarevich group involves looking at other ones like it. For example, 3x cubed plus 4y cubed plus 5z cubed equals 0, which is not technically an elliptic curve. It's a genus 1 curve, but it's not an elliptic curve precisely because it has no points. And the Tate-Shafarevich group, one other way of describing it is in terms of these curves that are genus 1 but don't have points. And by assembling these together, you can make the Tate-Shafarevich group, and that's reflected in the Selmer group. It's too intricate to explain in words, but it's another point of view. I gave it in the more modern terminology in terms of extensions. The older terminology was in these twisted forms.
Okay.
So what you proved in the very end is by now called, a special part of the modularity conjecture. In order to somehow trying to explain it, one has to start with modular forms and how modular forms can be used to generate elliptic curves. Could you give us a short account on this topic?
Elliptic curve we've described as an equation y squared equals x cubed plus ax plus b. And the a and b we're assuming to be rational numbers. So, as I said, at the beginning of the 19th century, you could describe the complex solutions to this. So you can actually describe these very, very nicely in terms of the Weierstrass P function, in terms of elliptic functions. But what we want is we want to actually find a completely different uniformization of this, which captures the fact that the A and B are rational numbers. So it's a parameterization just of the rational elliptic curves. And because it captures the fact that it's defined over the rationals, it gives you a much better hold on solutions over the rationals than the elliptic functions do, which somehow only really sees the elliptic complex structure. And the place it comes from are modular forms or modular curves. So to describe modular functions first. So we're used to functions which satisfy the relation of being invariants under translation. Every time we write down a Fourier series, we have a function which is invariant under translation. Modular functions are ones which are invariant under the action of a much bigger group, usually a subgroup of SL2 of the integers, of SL2Z. So you would ask for a function in one complex variable, usually on the upper half plane, which satisfies f of z, f of z, is the same as f of az plus b over cz plus d. Or more generally, is that times the power of cz plus d. So these are called modular functions, were extensively studied in the 19th century. And they hold the key to this arithmetic. And the way they hold the key is, perhaps the simplest way to describe it is because we have an action of SL2Z on the upper half plane, by this action Z goes to AZ plus B over CZ plus D, we can look at the quotient H mod this action, and you can give that the structure of a curve. In fact, it's naturally got the structure of a curve over the rational numbers. If you take a subgroup of SL2Z, which is what's called a congruent subgroup, so it's defined by, say, the C value being divisible by n, then you call the curve a modular curve of level n. And the modularity conjecture asserts that every elliptic curve over the rationals is actually a quotient of one of these modular curves for some number n. So it gives you a uniformization of elliptic curves by these other entities, these modular curves, which on the face of it might seem you're losing because this is a higher genus curve, it's more complicated, but it actually has a lot more structure because it's a moduli space.
And that's a very, very powerful tool.
And that's a very powerful tool, yeah. And you have function theory, you have a lot of tools for that.
But did Taniyama, the young Japanese mathematician that first sort of conjecture or suggested this thing, did he have this, his conjecture was more vague, I guess? His
was more vague, so he didn't pin it down to a function invariant under the modular group. I forget exactly what he did. It was invariant under some kind of group, but I forget exactly what kind of group he was predicting. But it wasn't as precise as that. I think it was originally in Japanese, so it probably wasn't circulated as widely as it might have been.
I see.
I think it was just notes after a conference in Japanese.
That was an incredibly audacious conjecture at the time, wasn't it?
Apparently, yes.
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 But then it caught the attention of, I mean, you told part of the story of Gerhard Frey in particular, who then came up with a conjecture relating Fermat's last theorem with the modularity conjecture.
Gerhard Frey showed that if you take a solution to the Fermat problem, a to the p plus b to the p equals c to the p, you make an elliptic curve y squared is x minus a to the p, x plus b to the p. Then the discriminant of that curve would end up being a perfect pth power. And if you think about what that means, if you assume this modularity conjecture, and you have to assume something slightly stronger as well, then it forces this elliptic curve actually to have the n that I spoke about equal to 1. But H mod SL2Z is a curve of genus 0. It has no elliptic curve quotient, so there wasn't anything there.
So that, in a sense, was the point of departure for your story. I mean, followed up, of course, by the work of Sarah and Ribbett, who made this more clear. So may I shortly summarize the story that then follows? So it has been told by you many times. It was even on a BBC feature. So you had moved to the US, to the United States, first to Harvard and then to Princeton University, becoming a professor there. And when Ribbett's result was out, you started to devote all your research time to working on a real attempt to solve the modularity conjecture for semi-stable curves, if I understand it correctly. And then follow 7 years of really hard work in isolation while you were working as a professor at Princeton University and while you were raising small kids. And then a proof seems to be accomplished by 1993, and your work culminates in a series of 3 talks at the Isaac Newton Institute in Cambridge, back in England. And as a result, you are celebrated by your peer mathematicians, and even the world press takes an interest in your results, which happens very rarely for a mathematical result. But then when your result is scrutinized by, in total, 6 referees for one of the very respected journals, it turns out there is a subtle gap in one of your arguments, and you are sent back to your desk. And then it took 14 months of hard and frustrating and sometimes really hard work and a heroic fight. In a sudden flash of insight, you find out that you can combine some of your previous attempts with new results to somehow circumvent the problem that occurred. And well, it turns out that this is just enough to prove what you really needed in order to get this part of the modularity conjecture that then encompassed Fermat's last theorem. What a relief that must have been. So, well, would you like to give a few comments to the story and some additions, or?
Yes, so in my terms of my own work, when I became a professional mathematician, I worked with Coates, I realized I really had to stop working on Fermat because it was time consuming, and I could see the last 100 years had done nothing. And I saw others, even very distinguished mathematicians, had come to grief on it. But this revelation, actually, when Frey came out with his result, I was a bit skeptical that the Serre part of the conjecture was going to be true, but when Ribbett proved it, then okay, now this is it. And it was, a long, hard struggle, but it was, in some sense, it's irresponsible to work on one problem to the exclusion of everything else, but it is the way I tend to do things. And I did feel with this problem, whereas Fermat was very narrow. I mean, it's one equation, whose solution may or may not help with anything else. The setting of the modularity conjecture was one of the big problems in number theory, and there was, it was a great thing to work on anyway, so it just was a tremendous opportunity. And I think when you're working on something like this, it takes many years to really build up the intuition, to see what kinds of things you need, what kinds of things a solution will depend on, and just to see, it's almost like discarding everything that you can't use and that won't work until your mind is so focused that even making a mistake, you've seen enough that you'll find another way to the end. Funnily enough, the mistaken argument, people have worked on that aspect of the argument, and quite recently they've actually shown that you can produce arguments very like that. In fact, for every neighboring case, it's the unique point that it doesn't seem to work for, and there's no real explanation. So the same kind of argument I was trying to use, using Euler systems and so on, has been made to work in every surrounding case. It's really extraordinary.
So no wonder that it escaped your attention in the first place.
You describe, I guess, this quest for the proof of the modularity theorem, that something like going into a mansion, and could you describe how it feels like?
Yes, I think when you take on a problem where it's not, you're trying to remove some condition that somebody had on a theorem, or you're trying to extend something. I started this off really in the dark. I had no prior insights how modularity conjecture might work or how you might approach it. I mean, one of the troubles with that problem, it's a little like the Riemann hypothesis, but perhaps even more so with that one, is you didn't even know what branch of mathematics the answer was coming from. I mean, there are three ways of formulating the problem. One is geometric, one is arithmetic, and one is analytic. And there were analysts with whom I wouldn't understand their techniques at all, who were trying to solve this problem. I think I was a little lucky, because my natural instinct was to be arithmetic, and I went straight for the arithmetic route, but I could have been wrong. I mean, you know, in some sense, the only known cases of this modularity conjecture are the cases of complex multiplication, and that proof is analytic, completely analytic. So I, partly out of necessity, I suppose, and partly because that's what I knew, so I could try it straight away. I went straight for an arithmetic approach. And I found it very useful to think about it in the way that I'd been studying Iwasawa theory. So with John Coates, I'd applied Iwasawa theory to elliptic curves. It's been his idea to use that. And then when I went to Harvard, I'd learned about Mesa's work, where he'd been studying the geometry of modular curves using a lot of the modern machinery. But there were certain ideas and techniques I could draw on from that I realized after a while I could actually use to make a beginning, some kind of entry into the problem.
Because before you started on the modularity theorem, you published a joint paper with Barry Maser,
Yes.
main theorem
Several
of
years.
Iwasawa.
Yes, exactly.
In this case, you needed over the rationals, right?
That was over the rationals. I did it with him, and then I'd worked myself on extending it to the case of the totally real.
So that turned out to be very, very useful when you then started with the...
It did. It gave me a starting point. It wasn't obvious at the time, but when I thought about it for a while, I realized that there might be a way to start it there.
And this result you extended to real fields, right? I mean, or
yes, I'd already done that before. Okay. Well, okay, let me be careful. So I'd basically done the extension to totally reals, but when I started working on the modularity conjecture, I realized I was going to need some time, and I wasn't going to be publishing very much. So my publication process of these results on the Iwasawa theory slowed down somewhat, covering my tracks a little bit.
You covered your tracks so that people...
Well, it wasn't to disguise it from other people. It was that I was supported by universities and financing foundations that expected results, not just attempts. So if I'd published all my things at once. Besides, I really, it was hard to distract myself from thinking about modularity to finish off preparing these results for publication. So most of that work was already...
I'm going to read you a quotation. The ramparts are raised all around, but enclosed in its last redoubt, the problem defends itself desperately. Who will be the fortunate genius who will lead the assault upon it or force it to capitulate?
It must be E.T. Bell, I suppose. Is it?
No, it's not. It is actually from Jean-Étienne Monticlat, Histoire des mathématiques. That's the first book in history of mathematics, written in the late 18th century. And it refers to the solvability or unsolvability of the quintic equation. And the general quintic equation, which of course Abel proved when he was 21 years old. That's here in Oslo, and he worked in complete isolation as far as mathematical things is concerned. In fact, this was Abel's obsession. I mean, he really delved into this, and he also got a false start. Thought he had proved that you could actually solve the quintic by radicals. And then he discovered his mistake, and he finally found the proof. Well, this problem was almost 300 years old, very, very famous. Well, if we now move fast forward 200 years, the same quotation could be used about the Fermat problem, which was 350 years old and which you solved. I mean, it's a very parallel story in many ways. Do you have any comments on this?
Yes, and in some sense, I do feel that Abel and then Galois were marking the transition in algebra from these equations which are solvable in some very simple way to equations which can't be solved by radicals. But this is an algebraic break with the quintic. And in some ways the whole trend in number theory now is the transition from basically abelian possibly solvable extensions to insolvable extensions. How do we do the arithmetic of insolvable extensions? Now, the modularity conjecture, I believe it was solved because we'd moved on from this original abelian situation to a non-abelian situation, and we're developing tools, the modularity and so on, which are non-abelian tools. So it's the same transition in number theory that he was making in algebra. It's the same transition in number theory which provides the tools for solving this equation. So I think it is very parallel.
Yes, it is a very, very ironic story because Abel, when he was 21 years old, he visited Copenhagen to visit Professor Degen, who was the leading mathematician in Scandinavia at the time. And Abel writes a letter to his mentor in Oslo, Holmboe, where he writes down 3 theorems about the Fermat theorem. One of them is not easy to prove, actually. He doesn't give any proof, and of course that's just a parenthesis today because I mean that wouldn't lead anywhere. But in the same letter, he says that he's desperate. He cannot understand why he tries to solve to divide the lemniscate arc in n equal pieces, and he gets an equation of degree n square, and he can't understand why n squared should be only n because there are only n points. And of course that is because you have double, periodicity. So when he got back to Oslo, he realized, and he sort of inverted and found the elliptic functions. And if you think about it, the thing that he did on the Fermat turned out to be completely, not valuable, but the thing that he did on the elliptic functions turned out to be the tool. Of course, Abel had no idea this was going to have anything to do with the arithmetic. So this story sort of tells that mathematics develops in mysterious ways.
It certainly does, yes.
So based on your experience, could you describe a little bit this interplay that we were already discussing between this hard and perseverant work on your desk on the one side, on the other hand, sometimes sudden flashes of insight that come out in a more relaxed atmosphere, and where it's difficult to see where they come from, but making it clear that you must have worked unconsciously further on what you have been doing with your pencil before.
Yeah, I think what you do is you get to a situation where you know a theory so well, and maybe there's more than one theory that you know so well, and you've seen every angle, you've tried lots of different routes, and you can just see you're connecting 5 dots. If they're sort of 5 places away from each other, you can't do. If they're 1 dot away, it's automatic, and somehow you just have developed such an intuition and understand these objects so well that you can see where they have to fit together. And this final insight is not something you rationally think out. I mean, there's this tremendous amount of work in this preparatory stage where you have to understand all the details, maybe some examples, and then when you've developed all this, then you let the mind relax, and then at some point maybe you go away and do something else for a little bit, you come back and suddenly it's all clear. Why did you not do that? And this is something the mind has. I remember this in a trivial example of this in non-mathematical terms. I remember once someone showed me some script, and it was some kind of Gothic script, and I couldn't make head or tail of it, and I was trying to understand a few letters, and I gave up. And then I came back half an hour later, and I could read the whole thing. And the mind somehow does this for you, and we don't quite know how, but we do know what you have to do to set up the conditions where it will happen.
This whole thing we're discussing now reminds me about one story about Abel. He came to Berlin and he lived with some Norwegian friends who were not mathematicians, but one of his friends told that Abel would typically wake up during the night, light a candle, and write down ideas that he woke up with. So I mean, apparently his mind was working.
Yes.
You know, yeah.
I do that, except I don't feel the need to write it down when I wake up with it, because I know I won't forget it. What I'm terrified is if I have an idea and I'm about to go to sleep, that I will not wake up with that idea. So then I have to write it down. But
okay.
So at the end of the day, are you most of all thinking in formulas or geometric pictures, or what is it you shape in your head?
yeah, it's not really geometric. I think it's patterns, and I think it's just parallels between situations I've seen elsewhere and the one I'm facing now, or just in a perfect world, what's it all pointing to? What are the ingredients that ought to go into this proof? What am I not using that I have? Sometimes it's just desperation. I assemble every piece of evidence I have, and that's all I've got, and I've got to work with that, and there's nothing else. I often feel that doing mathematics, it's like you're a squirrel and you're being chased, and there's these, or even there's some nuts up the top of a very tall tree, but there are several trees, you don't know which one. And what you do, you run up one, and then you think, oh no, it doesn't look good, this one. You go down, up another one, and you spend your whole life going up and down these trees, but you only go up to 30 feet. Now, if someone told you the rest of the trees are, it's not up them, you've only got one tree left, you just keep going and you find it. So in some sense, it's ruling out the wrong things that is really crucial. And if you just believe in your intuition and you stick with your one tree, you will find it.
Talking about more general thing in mathematics, there's a citation of Felix Klein. He said that mathematics develops as old results are being understood and illuminated by new methods and insights. From this, new problems naturally arise. And Hilbert said something like, good problems are the lifeblood of mathematics. Do you subscribe to these things?
I certainly agree with Hilbert, yes. Yeah. Good problems are the lifeblood of mathematics. I think you can see in our century this, I mean, for me, obviously, modularity conjecture, but the whole Langlands program, Birch and Swinnerton-Dyer conjecture, these problems give you a very clear focus on what we should try and achieve. The Weil conjectures on curves over finite curves and then varieties over finite fields. These problems somehow concentrate the mind and also simplify our goals in mathematics. Otherwise we can get very, very spread out and we're not sure what's a value, what's not a value.
Do we have as good problems today as we had when Hilbert gave his 23?
I think so, yes.
Okay.
I think the Riemann hypothesis is the single greatest problem that I understand. And it's sometimes hard to think exactly why that is, but I do believe it's actually solving that will help solve some of these other problems. And then, of course, I have a very personal attachment to the Birch and Swinnerton-Dyer conjecture.
Of course. It's sort of intuition can fail us. I mean, Hilbert thought that the Riemann hypothesis would be solved within his lifetime. And there was another problem he thought would never be solved in his lifetime, which Gelfond, so our intuition can be wrong,
That's right. I'm not surprised he felt that way. I mean, one does feel the Riemann hypothesis is such a clear statement, and we have the analogues in function fields, sort of understand why it's true there. We ought to be able to translate it. Of course, many people have tried and failed.
Yes. Oh, yes.
But I would still myself expect it to be solved before the Birch and Swinnerton-Dyer conjecture.
Are you interested in other sciences apart from mathematics?
I'd say somewhat, but not, again, I'm not going to devote, these are things I do to relax, so I don't like them to be too close to mathematics. So if it's something like animal behavior or astrophysics or something from a qualitative point of view, yes, I certainly enjoy reading about those or about what machines are capable of, sort of popular science, but I'm not going to spend my time learning details of string theory.
That would be too much.
I'm too focused to be willing to do that. Not that I wouldn't be interested, but this is my choice.
I would like to thank you very much for this wonderful interview. And this is first of all on behalf of the two of us, but moreover also on behalf of the Norwegian, the Danish and the European Mathematical Society. Thank you so much.
Thank you very much.